Back to another video, guys. You're on Physics with Daniel Dallas, and we are open new series dedicated to electricity. So that's a solid theoretical basis. I think it will be useful in different aspects and on different programs if you A-level student, IB students, or even G Main, G Advanced in Physics. So that's will be relevant to you. So I'll just keep the basics dedicated to static electricity, maybe just I'll fill this gap later on. But today we'll be talking about carrier drift current in conductors. So I'm not going to mention semiconductors and insulators, obviously, as non-conductors. So we'll be talking about conductors, but as you understand, conductors might be in different state of matter. So it might be solids, might be liquid state, might be gases and plasma, as basically overheated gas. So we'll just go through and explore the main ideas that lay behind how current can be generated. So we'll touch the concept of drift velocity. So we explain the factors why actually on a free run electrons can reach much higher velocity than while in, for example, in conductors it's limited to certain values. All right, and we'll approach the main fact that drift velocity will be dependent on external electric field being applied to your pattern, to your substance where you expect to have a current flow. All right, so if you're ready, grab your notes, grab your pens, and let's get started. So right, we are be talking about charge carriers in conductors, because we are going to consider conductors. I skip semiconductors in this video. And I just classify conductors according to their states, a state of the substance. So that means we can find solids, liquids, and gases. So gases. So plasma, talking about plasma, I will include it within gases category because plasma is really overheated gas, so that there are no neutral atoms, and all atoms are split between positive and negative ions. So I'll show you what ions are in the concept of liquids and within the solid group. And let's start with the solid one. So because we're talking about charge carriers in conductors, so all that are conductors. First of all, we'll be talking about metals like aluminum, copper, wire, and let's consider a piece of wire. So here is the wire. Of course, metals are characterized by a specific structure, what is called lattice structure, so that we can find atoms within nodes of this lattice. But right now, without any external electric field, they're neutrals. So those are atoms and they are neutrals. How to create current in solids? Of course, we need to plug this piece of wire to the cell or to battery cells, basically to the source of their electric field, and hence we can say that once it's plugged, there is electric field directed, let's say, from left to right. So that means we have positive terminal being plugged from the left side. So that's positive terminal, and we have electric field strands. And now let's go back to chemical properties of metals. So any metal, according to, let's say, planetary model of Rutherford, contains neutrons and protons and electrons spinning around. That's any, let's say, this is the model of any substance, of any atom. So those electrons, there might be several shells, but we will consider outer shell, and That means atoms, according to properties, chemical properties, they can easily give outer shell electrons out. On the effect of the electric field, there is electric force, and so this is the starting point when the electric fields interact with atoms. Those electrons can be easily torn from atoms, making them positive ions. So those electrons now in between lattice, somewhere in between. Of course, those electrons, due to the fact they're under electric field, are exposed by the electric force, and this electric force applied to each electrons make them flow to the direction of the positive terminals, basically from to the left side of this wire. This is electric force, exonym, and if we multiply by electric charge, electron charge, we'll get the electric force, and as a result, we'll get acceleration. So basically, they will gain in velocity due to external force. But this is external electric field, and this is external force. Because we left atoms now without external electrons, those atoms becomes positive ions. So that means right now, mostly in lattice, only positive ions left. So that means we have ions in the nodes of this lattice. So this lattice, okay? So what it means? It means that each electron will interact with those positive ions. And of course, that will cause their different force applied to it. So if you consider electron, it will interact with this ion, with this ion, with this ion. However, if we apply enough electric field strengths so that the most force, if you just consider the force body diagram for this for each electron, so on average, the force will be directed towards positive terminal. So that means for a majority of electrons, their average acceleration will be directed towards positive terminal. However, there might be intervals of time when this electrons is actually deaccelerating and then accelerating again. But in average, we can say that speed or velocity, what is called drift, will be directed in average towards the positive terminal. So that's how we can create a current. And those substances represented by electronic gas will be moving and in lattice positive ions interacting with them. And of course, the more temperature, the more oscillation of those ions, and hence their more interaction with electrons. There are higher chance to scatter on positive ions, hence losing energy, losing kinetic energy, and hence decreasing the velocity of the drifts. But in average, we have this sort of picture here in metals, and we have electronic gas just moving towards the positive terminal. Of course, if we consider metals and we exclude lattice, so all those electronic gas will accelerate to real great speeds. So, but on the way it interacts constantly and permanently, so that significantly decreasing the speed of free motion in comparison with that. So that means the velocity of the drift is quite small. Okay, if we go to liquids, the story about liquids a bit different one. Here, all those electrons in metals were basically were given out by the external electric field. What about liquids? In liquids, we have another way how we can arrange, I just erase for a while. Okay, I'll erase that. So, and consider liquids over there. So in liquids, we have a bit different process, the lay behind. So here in liquids, we have distilled water and some solution inside, because distilled water is non-conductor, while some salt dissolved in it, like sodium, for example, we have sodium chloride here and here. And once put into distilled water, it becomes actually split on positive and negative ions. And by which process? That's pretty simple. So metal, because sodium is metal while chlorine not metal, is non-metal, sodium will easily give electrons off. So that means it will lose electron, while chlorine will catch and trap it within structure. So we will have basically, most of the cases, we have positive and negative ions represented by sodium as metal and non-metallic chemical elements like chlorine, in this case non-metal. So it will lead to the ions structure, but because in liquids the degree of relocation is quite higher than in metals, so all those ions will be freely to move if we apply external electric fields. So basically, if we apply electric fields through the substance, we'll make positive ion moving towards the negative electrode or negative plates, what is called cathodes in this case, cathodes, while positive electrode, what is called anodes, will be the final destination for negative ions, like for chlorine. So that means we will have we'll have current in both ways, while in metals, current represented by electrons, while here in liquids, the current will be represented by both positive and negative ions, and the total current will be superposition of them. Okay, it means that actually if we put electrodes within the substance, chlorine will cover cathode, while sodium will cover cathode, while chlorine cover anode. So this process is very useful. It's called electrolysis, and by covering the process of covering the electrode by layer of the metal is called electrolysis, and it's very useful. It finds its implementation if you want to evenly cover the surface of the metal of the surface of some substance that you need to cover with the metal. All right, so that's what's happening in liquids. Let's go to gases and consider what are the main processes that takes place there. So if we're talking about gases, so here, just in comparison, so we're talking about gases at room temperature, so around 3000 kelvins. There are no ions. There might be actually there might be ions, but the concentration is quite small. It's just negligible. However, here, if we apply some external source of energy, like radiation, let's say radiation, by probably applying X-rays or applying ultraviolet radiation, there is the high chance, so high frequency radiation, there is the high chance that outer shell electrons of the atom of the gas inside, let's say gas tube, so this is the gas tube, outer shell electrons will leave the orbitals and becomes actually electron gas. Okay, so that means that atom becomes positive ion. While those electrons can be trapped, there might be like several cases, so it might interact with other neutral atom, and this Levene process sometimes, and it can generate more electrons on the way. However, there might be another process when those electrons were caught by the neutral atoms and hence becomes negative ions. But in general case, we'll have majority of positive and negative ions in that case. And they become the main charge carriers within gas. But one more time, so you need extra source of energy like radiation. Okay, so that's one aspect how you can create the conductivity of gas in that case, in this manner. So, and if we apply again potential difference or external electric field, so all those ions will move like similar what you have in liquids. However, their degree of freedom for ions is much more than in the liquids, because the average the average distance they can travel. For example, each particular ion can travel between collisions, consecutive collisions, much higher, definitely. That's what is called the free length between two consecutive collisions. And it will cause, I think, greater drift speed or drift velocity and external electric field. We can create current in this manner. Okay, so what about electrons? There is the case that electrons be there, and sometimes electrons can be trapped by negative, but let's say by positive ions backward, and this process what is called recombination process. So basically you have generation due to X-rays, due to external radiation. So that's how ions appears, external source of energy, and also the process of recombination. So recombination is the process of recombination is basically the process when your electrons are trapped by positive ions, and hence it becomes neutral atom, so that there is no free charge carrier anymore. So this process basically kill ions, and that means it's, in terms of the current, it decreased the current, so it basically decreased the concentration of ions. So process of generation due to external X-rays, and recombination as the negative process in terms of creating charge carriers in gas are two main processes that occur in gases. All right. So, talking about plasma, we also can say that due to the high temperature, there will be the pictures on plasma. In plasma, due to the high temperature, there will be positive and negative ions mostly. And that means that plasma is the good conductor, so you can use that in order to, by applying electric field again, in order to create currents. All right, so we talk about different charge carriers in conductors, and we also found out the circumstances under which solid state, liquid state, and gas state become good conductors. So that means we can simply use this idea and understanding of which particles are free and free charge carriers. We'll just move on and consider the aspects, I think, using the gas model and gas state. We'll consider very interesting phenomenon, how the drift velocity is depending on electric fields. So the next step is to consider how the drift velocity depending on external electric field applied. Okay, and that's the next step into consideration.